A new telescope built to track fast-moving space objects in Chile has caught a comet from beyond the solar system moving across the sky.
Every so often, something wanders in from the deep dark between the stars and refuses to behave. In 2025, astronomers spotted 3I Atlas.
On the 1st of July, NASA detected a mysterious object speeding toward Earth, and some actual bona fide experts think it might not be your typical space rock or maybe any kind of rock or a natural phenomenon at all.
Only the third confirmed visitor from another star system. It looks like a comet. It acts like a comet. And yet, it doesn't line up cleanly with what we know. Tonight, we're going to unpack why scientists are excited and a little uneasy about what 3I Atlas really is, what its odd chemistry implies, and what answers the next few months might finally reveal. Start with the basics. 3I Atlas isn't bound to the sun. Its path is hyperbolic, an open-ended sling past our system before it vanishes into interstellar night. That's how we know it's not from here. It was first seen by an Atlas telescope in Chile on July 1, 2025, and Orbital solutions traced it backward to a birth far beyond the Oort cloud, perhaps in the Milky Way's ancient thick disk. Older, colder and poorer in heavy elements than the neighborhood that built our own planets. It will skim its closest point to the sun around October 29, 2025, safely between Earth and Mars, then fade. It's a cameo, not a residency. And that brevity is part of the tension. We have one pass to learn everything we can. Early images ticked familiar boxes: a condensed head, a growing coma, a tail that lengthened as sunlight warmed the nucleus. But the spectra, our chemical fingerprints, threw curveballs. Using the James Webb Space Telescope, teams reported a coma unusually rich in carbon dioxide compared to water vapor, one of the highest CO2 to H2O ratios ever measured in a comet. That's not business as usual. Most comets we know are water-driven near the sun, with CO2 playing a supporting role. Here, CO2 seems to be the star. Instantly, questions multiplied. Did 3I Atlas form where CO2 ice is abundant, farther from its original star? Or did radiation in some harsh environment alter its chemistry over billions of years? The answer matters, because 3I Atlas isn't just a traveler. It's a sample jar from a different planetary nursery. Then there's the way it scatters sunlight. Polarimetry, the study of how light is polarized after bouncing off dust, lets us probe grain size, composition, and structure. For 3I Atlas, observers reported an unusually deep, narrow negative polarization branch at small phase angles. In plain language, the light is coming back in a way that doesn't match the average behavior of familiar comets. We've been surprised by an interstellar object's polarization once before. 2I Borisov looked different than typical solar system comets, but 3I Atlas appears to be strange in a new direction. If the dust grains are textured or sized in unfamiliar ways, that could point to formation conditions we don't commonly see at home. Or, less dramatically, it could hint at an unusual size distribution being lofted off the nucleus right now. Either way, it's a clue that this isn't just another dirty snowball. So is this dust exotic or just temporary? The next few weeks might decide. Size and mass estimates for fast, distant objects are slippery, but this is where unease creeps in. Then comes the question of weight. Most comets jitter as jets of gas kick them around. 3I Atlas doesn't. It vents material, but its path stays rock steady, as if the nucleus is far heavier than expected. If that's true, we're looking at a body denser, larger, and more inert than the comets we know. On paper, it's just a detail. In practice, it's unsettling. Comets usually self-thrust a bit as jets of gas and dust act like tiny rockets. If you don't see that, yet you still see outgassing, one interpretation is that the nucleus is simply hefty. Others counter that geometry, jet direction, or timing could mask subtle accelerations. The debate is live in preprints and posts, with high-profile voices arguing that the lack of detected non-gravitational wiggles implies a denser, larger, or more inert body than expected. That's not inherently sinister, it's just odd enough to keep people up at night running models. If the models are right, then this isn't just another dirty snowball, it's something stranger. Whenever an interstellar object acts weird, headlines follow. A controversial paper this summer gamed out a speculative scenario in which an artificial object could tweak its path and even rendezvous after perihelion. NASA and many researchers quickly poured cold water on the leap from anomaly to agency, reminding everyone that extraordinary claims need extraordinary evidence, and that we've collected no radio signals, no engineered shapes, no propulsion signatures, nothing that requires technology to explain. Skepticism here isn't dogma. It's the guardrail that keeps curiosity from careening into certainty. The fear for professionals isn't aliens. It's that hype drowns out the slow, careful work that actually answers the question. There's also anxiety about what we might miss. 3I Atlas's path takes it behind the Sun from Earth's perspective near its liveliest phase, the weeks around perihelion. That solar glare is a brick wall. Teams are juggling every telescope they can, but there will be stretches where we're effectively blind. Add in solar activity, a coronal mass ejection slamming into a fresh, volatile coma, and you have a natural experiment we can't fully control. Is the coma driven mostly by CO2 because an insulating crust is throttling water, or because we're catching the object at a specific thermal state? If a CME rips through it, does the tail morph in ways that reveal grain sizes or jet structure we'd otherwise miss? The timing could be a gift, showing us how interstellar comets react under solar fire, or it could scramble the data so badly we never get a clean answer. Underneath the headline grabbing speculation is a quieter, deeper fear that we may need to redraw parts of the planetary formation playbook. If 3I Atlas truly is CO2 dominated relative to water, and if that turns out to be common among interstellar comets, then the average building blocks beyond our solar system might be chemically different than the ones that seeded Earth. That ripples outward. How quickly do giant planets gather gas if their seeds are rich in volatiles we don't usually prioritize? How fast can worlds form in disks around more massive stars if they're capturing swarms of interstellar debris? Some researchers even suggest that captured interstellar bodies could act as planet-making seeds inside young disks, accelerating growth before the gas disappears. If that picture is right, then visitors like 3I Atlas aren't just curiosities. They're fossils of a process we still don't fully understand. Strip away the noise, and a few anchors remain. It's interstellar, hyperbolic orbit, inbound speed, outbound fate. It is active. Coma and tail confirmed, growing as sunlight ramps up. It is chemically unusual by our standards. CO2 loud, water comparatively quiet in JWST spectra at a few astronomical units. It appears, at least so far, not to be piloting itself. No confirmed non-gravitational acceleration beyond what outgassing would suggest, and certainly no radio beacons. Those data points don't solve the mystery, but they box it in. The task now is to fill that box with more measurements, better photometry, more spectra across wavelengths, tighter astrometry to chase tiny course changes that, if real, would speak volumes. The simplest, most decisive tests aren't very flashy. If we track its position against a purely gravity-driven trajectory and the residuals stay quiet while the coma remains bright, the case for an unusually massive or unusually symmetric outgassing source strengthens. If JWST keeps seeing CO2 dominate even as the comet warms, then the crust choking off water models will need to adjust. If polarimetry evolves from peculiar toward a more typical profile with changing phase angle, then the dust may not be alien, just transiently strange. And if a CME scours the coma and the tail rebuilds with different grain properties, we'll get a before and after snapshot few missions ever deliver. Each of those outcomes points toward a more prosaic, but still thrilling, conclusion. 3I Atlas broadens what normal can mean for comets born under other suns. Imagine the cautious view proves correct. A massive ancient comet drifts in, shaped by a strange corner of the galaxy, its dust scattering light oddly, its gases richer in CO2. That alone would rewrite our models, forcing us to accept a whole new class of interstellar wanderers. Next time, we'd be ready. Now picture the daring scenario. Not aliens, but something equally profound. Interstellar bodies as architects of worlds. Their chemistry seeding planets, reshaping disks, making our solar system the outlier. That would change how we search for life. The danger isn't invasion. It's realizing we've built our expectations too narrowly, while the galaxy writes its stories with colors we've barely begun to notice. Now, if you've seen the scarier headlines, you've also seen the corrections. NASA and many astronomers have had to repeatedly remind the public that 3I Atlas is not an alien spacecraft, that it poses no threat, and that the sensible response is to measure, not panic. That tension between curiosity and sensationalism always flares around interstellar visitors because they arrive as mysteries on a countdown clock. We can't schedule a second look. We can only sprint to understand before the night closes. The fear, in other words, is missing something important. Not because it was hidden, but because we were distracted. In the near term, keep an eye on 3 threads. First, the astrometric fits. If teams continue to report no detectable non-gravitational push despite a lively coma, expect renewed arguments about mass and structure. Second, the chemistry. JWST and ground infrared could confirm whether CO2 dominance holds or evolves, and whether faint companions like CO or OCS hint at deeper stories in the nucleus. Third, the polarimetry. Does that strange negative polarization branch persist as the geometry changes, or does it relax toward familiar comet behavior? Each result narrows the field of possible origins and nudges what it really is, from speculation toward definition. In a few months, 3I Atlas will vanish, just another streak of light slipping back into the dark. But what it leaves behind could outlast us all. Clues about how worlds form, how chemistry shapes life, and whether our solar system is ordinary or rare. That's the real fear. Not aliens, not impact, but missing the one chance to hear its story. Because once it's gone forever. And if the universe keeps sending messengers like this, the only question is whether humanity will be wise enough to listen. To keep exploring mysteries like this one, subscribe, tap the bell, and share your thoughts below. What do you think 3I Atlas really is?